Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 5.5.2, incidence questions. Okay, so we're going to consider another question, which is solved by a Z-module map. So last time we had a Z-module map that preserved structure, and in fact free Z-module structure, so we could represent it as a matrix. This one we can also represent as a matrix. And so it's a different question. This question has to do with incidence. Incidence meaning like edge hitting vertex. Before, for adjacent, it just means vertices that had edge between them. Incidence means like a hit, like an edge hitting a vertex. Okay, so here's the question. Given a collection of directed edges, what is the total net edge incidence rate of flow on all the vertices due to these edges? So here, it looks like we're going to be going from edges now. So some kind of module that represents, before like we had like Z4, but here we're going to have something that deals with edges. So some kind of module that represents edges, and that's going to be input, and output is going to be some information about vertices. So there are 4 vertices, so something in Z4. So the codomain should be Z4 and representing vertices, and the domain representing E edges. Well, how many edges are there? There are 9 edges. So it looks like we're going to be going from Z9 to Z4. Z4 is codomain, Z9 is domain. Okay. So, well, how are we going to compute this, and what does this mean? So let's see. Like right here, for instance, we have an arrow coming into this vertex and one going away. If it comes into, we're going to call that a +1 hit, or incidence, +1 hit going away, like a -1. So the total net incidence or rate of flow right here, we just add these little numbers together, +1, +1, -1, and we end up getting +1. So the incidence right here is 1. So given a collection of edges, we're going to say, okay, what kind of incidence does this cause at each vertex? So like, for instance, what if we selected like E5, E8, and E7? All right, so just those ones. Let's just think about it. E5, E8, and E7. Then let's see, what kind of incidence do we get? So what kind of incidence do we end up getting at vertex 1? Okay, and so this is going to be the image of, so okay, let's see here. Yeah, at 1. So let's just answer the question for 1 to kind of get in the sense. So yeah, so at 1, we have a net incidence of, let's see, if we just did, so we're just doing this edge, and this edge. It looks like we, in and out, looks like we have a net incidence of 0. What about the edge at 2? Well, we're ignoring all these edges, so really these edges don't create anything over there, so it's just 0. The incidence at 3 looks like in and out, so it's just 0. And what about the incidence at 4? Looks like we're in and out, so just with those edges, so we're 0. So really, this particular collection of edges produce that kind of incidence. Now, we could have thrown in another one. Let's see, thrown in something like that, and let's see how that changes things. And let's see here. Let's think about net incidence again. What's the net incidence at 1 by this? Let's see. Well, here we have 2 going out and 1 going in. So it looks like, and going out is like a negative. So it's like a net -1 incidence at the first vertex. Net incidence at 2 is again 0. Net incidence at 3, well, let's see, we have we have 2 going in and 1 going out, so it would be an incidence of +1. And then what about at 4? So in and out, so it looks like a 0. So it looks like this right here would be, given this particular collection, would be the incidence given there. Now we can also double up an edge here and do multiplicities. Like, so we have our different edges, we have 9 of them. So we have like, so the input is like a collection, right? But you can actually double up on one of these things. We're going to have a 9 tuple. And let's suppose for one of these, suppose we have, so this is like, in this particular case, what if we did, what if we doubled up on this one? So we can double up. So like we'd like think of this edge happening twice and then look at the incidence that happens from that. So if we think of this edge as happening twice, so that's the 4th guy. So 1, 2, 3, 4. So right here, we put a 2 down. And then in these other, let's see, and then we have, so this is so 1, 2, 3, 4. Okay. So 2, and then let's do, look like the Z5. So 4, 5 would be a, so we're just having one of those edges. Or E, we're skipping E6, then going to E7. So E6 is not there, but E7 we're using. And then E8 we're using, and we're not using E9. And let's see, I think that's all we're using. Okay. So this is like the input. So this is the input, and what would the output be? Well, it would be let's see, it'd be the same as this, except we change the result except we change the result a little bit because we've kind of doubled up here. Let's see how it changes. Okay, well, now we have 2 coming in at 3 and 2 going. It's no, actually we have 3 going in. So let's see, we have this one coming in, that one coming in, that one coming in, 1 going out. It's 3 coming in. So that looks like that would be a +2 net. And what about up here? What would that be? Here coming, so we have 1 coming in and 3 going out. So that would be a net of -2, actually. All right, now, okay. So, and that would be it, because everything else again was at the different locations at 4 at 0, 2. Okay, so we're good. So that's kind of a little description for what we're going to be looking at. So the question is, given a collection of edges that lives in with multiplicity. So with multiplicity now, integer multiplicity, we'll throw that into Z9. And then we have a map from Z9 over to Z4 because we have information for each vertex for the net incidence. And that's what it's a function of, okay? And we can represent it as a matrix. It's a Z-module map. It preserves Z-module structure. Okay, so that's kind of what we're looking at. And here's an example right here. Like, where does answer the question just for E1? So for E1, if we go look up here and look at this for edge 1 is right here. So let's answer the question just for edge 1. Well, that creates, so there's no other edges. All the other edges are gone. Well, that's going to create a -1 and a +1 only. A +1 at 2 and a -1 at 1 we're coming out of when we're going into. So that it's pretty easy to do it for just one thing at a time. So the image of a single edge always has just a 1 and a -1 and the rest zeros. So just denoting what the edge is doing, like where the edge comes from and where it's going to. So this edge 1 goes from V1 to V2, vertex 1 to V2. And so we can see that from vertex 1 to vertex 2. And the same thing for E3 and E2. That is why we see these three columns looking the same. So it's really information about what's happening at the vertices for each edge individually. And you put that into columns, and then you run that through a matrix multiplication, and you can get it for a whole collection of edges. So the image of E4, so E4 comes from vertex 1 and ends at vertex 3, and you can see that right here, from vertex 1 and ends at vertex 3. That's E4. So if we wanted to see where a collection with multiplicity of edges, what kind of incidence it creates on the different vertices, then we could do this as follows. We could run matrix multiply. It'd have to be a 9 tuple because the input lives in Z9. So the output is in Z4. That's why the columns, there's only 4 things in each column, because the images of each one of these guys lives in Z4. But there are 9 columns, which represents a domain of Z9. So 9 columns means the domain, and 4 rows kind of signifies the codomain. So we would input something here and then just matrix multiply it. So if we had, like, for instance, what if we were just doing like edges 1 and 2? So if we just did edge 1 and edge 2, and then we have zeros. Okay, so we have 9 zeros coming down. Then this just means we add to get, we say 1 times the first guy plus 1 times the second guy here. And doing that would output, for instance, -2 and 2, and then zeros going down, which means, or actually, oh, wait a minute, I wrote that wrong because I only want, what is the image? The image lives in Z4, so it's just 2 zeros going down because there's only 4 vertices to worry about. I mean, this column was for edges, this one is for vertices. So -2, 2, that just has to do with adding these first 2 columns together. That's what this means here in the matrix multiplication. We get -2, 2. That means that if we just doubled up edge 1 and doubled up edge 2, then our net incidences, let's see, no, not double up. I mean, if we just took the collection of just E1 and E2, that's what I meant. Take the collection of just edges E1 and E2, then these would be the net incidences. Let's take a look at that. Okay, so let's come up here and look at that. So what if we just took E1 and E2 only and just ignored everything else? Notice that there would be a +2 incidence here and a -2 incidence there. It should be clear, and we can actually get that via matrix multiplication right here. Okay, just one little note at the end. Let's suppose the incidence matrix is given by a map G. So G of E1, so E1 is edge 1. We could write this as simply V2 minus V1. Why is that? Because, well, V2 is represented right here as that vertex minus V1. Quite literally, you could think of these V1, V2, V3, V4 as being like the standard basis tuples in the codomain. And if you did that, well, we can just write this out. If you did that, then you could think of V2. So let's think about this. V2 is quite literally 0, 1, 0, 0. And V1 is 1, 0, 0, 0. And then if you subtract these two, notice you end up getting -1, 1, 0, 0, which is the same as this first column, which is G of E1. So we could actually just but you could just have gotten that by just thinking there's a 1 here, so let's just attach that with V2. There's a -1 here, attach that with V1, and just write down simply in terms of the standard basis tuples, just write down the image of E1 is simply V2 minus V1. We can do that very, very nice, neatly. And in general, if A and B are vertices, we can just simply say that the image of that particular edge under the oriented incidence map, so this is oriented because we have direction, would just be the vertex that we hit minus at the tip minus the vertex at the tail. And we will end right there. Thank you for watching.